Okay, so welcome again in this 11th lecture of the course. So let me write down here, lecture 11. I remind you that we are now working and we are entering the realm of hyperelasticity. So essentially, elasticity. I remind you that essentially what we've done in the last lecture is essentially to introduce the concept of strain energy density. And we've already started so initially we said that the energy should depend on the whole deformation gradient. As we will now see, this is not completely true, because through objectivity, in fact, these dependence must be reduced. So it won't be on the whole 9 components of the gradient of deformation, but only on 6 of such components. And today we will also start to introduce another very important concept, which is the concept of material symmetry. And through material symmetry, we can actually qualify the differences between a solid, between a fluid, or for example, an anisotropic solid. So, with this in mind, let me start a little recap of the concepts of the last time. Now, let me just say very briefly, we know very well that if we have a spring, and this spring is being shortened or elongated, and the amount of shortening or elongation is simply x, we know that the energy in the spring is u of x equal to, or rather, let me call it with the same letter, w of x, that we use in the 3D. This is equal to 1/2 of the elastic stiffness of the spring, x squared. And we know that the force in the spring is equal to the derivative of w relative to x, right? And everybody knows that this is equal to kx. So the force in this case, for example, is a force applied to the two extremities of the spring. I'm using lowercase f to avoid confusion with the gradient of deformation. So what we are starting to understand is that things are not different when we discuss the deformation of a body. So in general, we will have a 3-dimensional body. This body deforms, and the amount of deformation is expressed by the gradient of deformation f. I simply denote it. Let me just do very briefly if I denote, okay, I use this color. If I denote the deformed configuration in this way, you take one potato and you deform it slightly in this way. Well, actually, it seems that I deformed the potato into an apple. I don't know, when I delete, I don't know if you can see what I do, but because probably the program avoids. But in any case, you see, this is the amount of deformation in this case, and this deformation is described by, we know well, the gradient of deformation f, which is equal to the gradient of chi. And well, just like in the one-dimensional example that I've denoted here, well, just like that, also in this case we have that an energy w depends on the deformation, but in this case the deformation is a function, is essentially also, by the way, notice please that these are 9 variables. 9 variables for each point, because this is a tensor, and this is a tensor with 9 entries. So this tensor, this is, you see, the complexity that we are introducing. Essentially, we pass from a one-dimensional case in which you only need one variable, which essentially is telling you the elongation. But in the 3-dimensional context, what we are starting to understand is that for each point of the body, you need to characterize the deformation, you need 9 entries. So in general, what we have discovered is that this energy characterizes the stress. And what we found in the last lecture is that if you do the derivatives of the energy, you obtain that Sij is equal to the derivative of W relative to Fji, right? And this is what we have put in say, connection with the with the fact that also in 1D the force is the derivative of energy, well, also in 3 dimensions the stress is the derivative of energy. So you see, this is just to create a bit of contextualization. We are actually trying to understand how now this function, what are the properties of this function. Now, in the last lecture we've discussed the issue of objectivity, but in the lecture of today I want to discuss how to reconstruct the function w of f when we want, for example, to characterize a piece of rubber, a piece of silicon. How do we construct this function? This function cannot be completely arbitrary. It has to fulfill specific requirements. And in particular, today, we want to introduce one of the basic axioms of mechanics. And this is the so-called axiom of invariance under rigid body motions. So what does it say, this axiom? Well, this axiom actually says the following. It is an axiom of mechanics that the material response should be, and here the key word that establishes a connection with what we've been saying in the last lecture, should be objective. So what does it mean? It essentially means that the material response of a body is unaffected by superposed rigid deformations. So this is, of course, we're calling now this, to be completely correct, we're calling these rigid body motions because, in fact, the way we're discussing these avoids the introduction of time, and we're not really seeing these superposed deformations as motions. What is written in this claim is even more general than what we've done in the last lecture, because what we have done in the last lecture, we've talked about invariance under rigid body deformations. In fact, the axiom is even more general, and it concerns the invariance under motions, okay? But this year we're cutting a little bit the program, and we decided to stay away from the inclusion of time. However, be aware that the real axiom of mechanics is really talking about motions, rigid body motions, so involving given velocity. So with this in mind, we essentially, what does it mean? This means essentially that two things have to happen. The strain energy function W must be equal to W star. So it means that the energy that we are including in this treatment, the energy at the basis of the theory of hyperelasticity, the volumetric energy W should be invariance, and also the stress vector, should be invariant for superposed motions, which means this stress vector, which you have denoted with Michel T of n, must be objective. So, it is my purpose in this lecture to explore what are the implications of these two requirements. So let me start with the first of them, which is the objectivity of the stress. So let me take into consideration objectivity of the traction vector. As we will see, this will lead to the objectivity requirement also for the stress tensor. What does it mean that the traction vector has to be objective? To understand, let's make a little drawing. Imagine to take a little block of material, and you've already seen with Michel when you did the introduction of the so-called Cauchy's theorem. And in the Cauchy's theorem, you've used this argument of the tetrahedron. Yes, imagine now that you're looking at the tetrahedron from one side. So imagine this is the body, for example, in its current configuration, and imagine, for example, that this is the unit normal going in this direction. Yes. So what you have seen with Michel is that the contact forces on this block is characterized by a traction vector, and this traction vector is the Cauchy, comes from the Cauchy theorem, and it is the traction vector relative to the normal n. Now, what happens if I subject this block to a rotation? Well, I just made a copy of that block, and I just want to rotate this, yes? So, well, here it becomes, to tell you the truth, I have no idea of how to work this, but at least it's a bit fun. So, because it doesn't stop. Okay, so imagine that this block is being rotated rigidly. You see, I have done a rigid rotation, and if I rotated this block, in fact, I should rotate also the letters. Let me delete these letters here. So at this point, I delete this letter, but you see what happens is that in this rotated configuration, well, the vector, the unit normal n, was rotated to the unit normal n star, and the traction vector t of n was rotated to the traction vector t star of n star. I'm sorry if it is getting very small, but I think it's clear. So what is remaining unchanged in these, if you see clearly, is that first of all, in the rigid rotation, the shape of this cube is not being changed. So in other words, this block, the rotated block RC star, is exactly of the same shape. But the requirement of objectivity involving the vectors defined on this body essentially traduce for what is relevant for us to the fact that this angle between these two vectors here has to be unchanged. So you see, essentially this is the requirement of objectivity in the traction vector. Let's try to analyze more in detail. What does it mean? So essentially it means that if you rotate the body, once you sit in the rotated configuration, well, also the contact forces exerted from the external environment to the body, onto the body, also they have to rotate of the same amount. Let's try to deduce the implications of this requirement in terms of stress tensor, even though we already know what are these implications. Well, first of all, I want you to notice that the unit normal n star, in this case, will be equal to, well, the matrix Q, which defines the rotation applied to the normal n. So Q is the gradient of the map between these two configurations. And the requirement, furthermore, of objectivity for the stress, for the traction vector, simply traduces into the requirement that T star, relative to the unit normal n star, so the rotated, has to be what? Well, also this should be the rotation of the traction vector relative to the original configuration. Now, by the way, first of all, I want you to remember that through the Cauchy theorem, we know that this last expression, yes? So this last expression, we know that through the Cauchy theorem, let me write it below. Now, first of all, for what concerns the left-hand side here, this is what? Well, by the Cauchy's theorem, this is equal to the stress tensor, Cauchy stress tensor in the rotated configuration applied to the unit normal, rotated normal, right? And for what concerns the right-hand side, well, we can write that this is equal to Q. And then what it is T? Well, T is simply equal to the Cauchy stress sigma applied to the unit normal in the non-rotated configuration. So what is in this expression how do we pull out the value of sigma star, which is the Cauchy stress in the rotated configuration? Well, in this expression here, sigma and sigma star, these are the Cauchy stress in the two configurations RC and in the configuration RC star respectively. So at this point we remember that actually n is equal to Qn. So let me replace in this expression, we obtain sigma star. So instead of n I put Q, and here I have n, and this is equal to Q, and then I have sigma n. Now what is important is that this expression has to hold for any unit normal, which means this expression has to hold when you look at this normal, but if, for example, you cut the body with another plane, it should hold with another normal. So this condition here has to hold for all n unit vectors. And this means that if this condition has to hold for any unit vector, this means that sigma star q has to be equal to q sigma. By the way, this has to be true for all q orthogonal, right? Because we want the objectivity to hold for any rotation orthogonal. Now, what does this expression mean in turn? Well, if in this expression here for example, multiply everything by Q transpose, so I put Q transpose here and Q transpose here. Since Q transpose is equal to the identity because this is a rotation, we finally obtain the requirement that the final implication of objectivity for the stress vector, and this final requirement reads that sigma star is equal to Q sigma Q transpose. Now you may have, based on the lecture of the last time, you can immediately recognize that this requirement boils down ultimately to the requirement that the stress tensor has to be objective. Stress tensor must be objective. Okay, so this is the first interesting characterization we did. We have imposed a requirement that the action of invariance tells you that the response of a body should no way be affected by superposed rigid motions. In our context, in which we don't have time, we shall say not motions, but rather we should say, I want to add it on top of motions here just to underline that we don't have time. So not that we don't have time as a variable. So instead of the motions, we will talk about deformations. But just be aware that this holds even more in general. So, and we have seen that this essentially boils down to two things. One thing is that the energy shall be invariant, and the second thing is that also the stress vector shall be invariant. Yes, should be objective. Sorry. So the invariance of the stress vector ultimately boils down to the requirement that in a well-done law that characterizes the material response of the body, the Cauchy stress should be an objective tensor. Okay, so this is the first implication. Let's now pass to the energy, and you will see there is a very, very important message hidden here. Let me now take into consideration the very interesting and relevant consequences of a second requirement, which is the objectivity of the strain energy. Now, this is very, very important, and in fact is closely related to the discussion we are doing, in which the main player, the main character of this play is represented by the strain energy. Now, what does it mean? Well, let's just go into the details. First of all, I remind you that in the rotated state, the gradient of deformation is written as QF. So if F is the deformation, I just remind you, I always draw this as a reminder of what we're doing. We have a reference configuration. We have a current configuration which is being deformed. I will never be able to draw again this, let me do another shape, sorry. So let me say, for example, that this is the deformed configuration and this is the rotated configuration. So essentially what we're doing here, this is the RC and this is RC star. So the deformation from this domain to this domain is F, and then we do rotation, which is capital Q, and then we go from here to here, which is F star. Yes, so essentially what we are requiring in terms of energy is that the invariance, the objectivity of a scalar function essentially boils down to the requirement that W should be equal to W star. But what does this mean? What does this imply? Well, this has to be true for all Q that orthogonal. Yeah, so it means all those tensor whose transpose is equal to its inverse, orthogonal. Now, let's be more precise on this front. So essentially this means that W of F must be equal to W star of F star, right? But we know an expression of this F star, and this expression can be brought to write that this must be equal to W of, well, instead of F star, we have to write the definition, which is equal to QF. So ultimately, and here we are, the implication of objectivity introduces into the requirement that W of F must be equal to W of QF, and we can box this because this is absolutely fundamental, and this has to be true. Clearly, this must hold for all deformations F and for all Q orthogonal. Okay? Now, this apparently naive little box is absolutely fundamental. Now, why that? And here we are back into the, if you remember, we did together the polar decomposition theorem, and the polar decomposition theorem comes back in this point. Why that? Well, first of all, let me just remind you, what did we say in the polar decomposition theorem? Well, there, polar, you see, the beauty of this subject is that all topics we treat, they're gonna come back into some other parts of the course. So nothing we're doing in this course is absolutely useless. All the topics are being nested one into the other. This makes the complexity of this subject, but also the beauty of it. So the polar decomposition theorem, if you remember, tells you that if you have F, gradient of deformation, so F is equal to the grad of chi, and where chi is a deformation, where we have seen that there exist, and they are unique, two tensors, and R and U, in which U is a symmetric, positive, definite tensor, and R is a rotation, or to be more precise, it is an orthogonal tensor with positive determinant. So with this in mind, we can actually do something. The requirement of objectivity for the strain energy, which is this one here, we can rewrite it in this way. We can say that, well, it must result that W of F must be equal to W. Well, instead of writing F now, I write that this has to be equal to Q. And here I have to write, well, instead of F, I write RU, which is the unique polar decomposition relative to F. But now, this is the magic. Since Q and Q is arbitrary, since Q is arbitrary, of course arbitrary rotation, we are free to choose, well, we're free to choose Q equal to R transpose. And where's the magic here? Well, if we do, just let me go down here, if we do, we get that this is equal to W, or instead of writing Q, I write R transpose R, and here I have U. But R is an orthogonal tensor. So what does this mean? Well, this means that, I don't know for what reason the pages are blinking. Maybe my iPad is complaining with me of something, but I don't know what. So I apologize for that. But since these two guys here, since R transpose is in fact the identity tensor, we end up with the fact that this is equal to W of U. So we ultimately can say that our requirement of the strain energy being objective, which is what we wrote here, the requirements that the strain energy is objective ultimately boils down into the following thing that I will now put in frame. So let me write it again. So essentially, we've written, we were able to find that W is objective. This means it can be rewritten as, well, the W of F shall only be a function of not everything, but just U. In other words, the objectivity requirement that we have obtained above by requiring that the strain energy function is unaltered, is unaffected by superposed rigid deformations, essentially means that the strain energy should not depend on the whole gradient of deformation F, but only on its symmetric positive definite counterpart. By the way, if you remember that the tensor U is in fact U squared is equal to what we called C, the objectivity requirement can be also be written as, so the objectivity is objective, can also be written as W of F equal to W, a function of C. Now, where's the advantage in all these? Well, the advantage is, in fact, rather consistent, but we will see that this simplification goes on. Why is it more simple? Well, let me do a remark. Well, the remark is that the matrix F has in general 9 components, right? Has in general 9 entries. So the specification of an energy function of the form W of F would lead us to the thought that to specify what is the state of the material response of the material response at a given point, you have to provide in that point 9 characteristics defining the deformation. However, the beauty of the interesting consequences of objectivity is that, in fact, the strain energy shall not depend on all these 9 entries, but on less entries. Why that? Well, I remind you that the tensor C, but if you prefer the tensor U, it's the same. The tensor C is equal to C transpose. So in other words, if you count the number of independent variables inside of this tensor, well, this will be only these entries, right? Because you see, all the others are being symmetrically transposed. So what it means that C has 6 entries. So contrary to F, which has 9 entries, C has 6 entries. Okay? So this is interesting because it essentially tells you that instead of depending on 9 as the general, don't forget, where did we get all this idea of the strain energy? It's always good to have in mind a global picture. The idea of energy comes from the idea of work. From work, we derive that when we are in the presence of a conservative environment, which means there is no dissipation, well, we get to the understanding, to the existence of a strain energy, which shall depend on F. However, through objectivity, we obtain that W should only depend not on the whole F, but only on the tensor C, which I remind you is equal to F transpose F. In other words, when you deform locally, the rotation relative to the deformation does not affect the material response of the body. So I would say this is really the rather important findings of these this first part of the lecture. So we are understanding that the the requirement of objectivity for the traction vector implies that the Cauchy stress should be objective, which means that sigma star is equal to q sigma q transpose for any superposed rigid motion, and the same requirement in terms of the strain energy leads to a strong simplification of the energy. Initially, we would think that this energy depends on the whole gradient of deformation. However, the objectivity poses the restriction that the energy should only depend on C. This is not surprising. Why? Because we have in fact seen that C is, in the lecture that we did together 2 weeks ago, we have seen that in fact C is embedding all the essential information on the deformations. Like, for example, if you want to measure lines, the variations of length, variations of angles, variations of areas, variations of volumes, all these pieces of information are included in the tensor C. So, in other words, it is not surprising to understand that the energy shall not depend on nothing else than C. Again, when you think about these things, think that this is not surprising at all. So, let me add another remark. Not surprising, because C embeds all info on deformations. So when we call about deformation, and to be more clear, I should say that C embeds all information on the stretch. So any local deformation changing the relative distance of point is solely measured by C. So this is very, very interesting to see that objectivity led us to this. Okay, so it means it's not surprising, because if you, for example, have a spring, yes, imagine the spring here, imagine a spring connecting 2 points. Well, if you rotate the spring and you bring it here, for example, you see the force in the spring shouldn't be affected by this rotation. And in fact, you're not changing the relative distance, for example, from point P and Q and point P and Q prime. The distance is unchanged. The material response is unchanged. This is precisely what is behind the idea of objectivity of the strain energy, a fundamental concept of continuum mechanics. Immediately below the concept of objectivity that holds for any material and for any situation, there is another absolutely fundamental concept. These are really deep concepts in the theory of elasticity, but more in general in the theory of continuum mechanics. This second concept takes the name of material symmetry. symmetry. So, what does this idea correspond about? Well, essentially, as we will now show, it boils down to characterize how really the fabric of a body is done. To introduce this concept, I want to make the following example. Let me take a piece of a tree, piece of wood, and let me take, for example, a cross section of a tree. So this is my tree. I take a cross section of the tree, and here it is. So, well, we know very well that in this tree, all the fibers of the tree will be aligned in this direction, right? All these fibers, well, they may not be completely and perfectly aligned in this way. In fact, there are interesting things to say, but let me just assume that the tree is being, for example, disposed in this configuration in a reference configuration, okay? So let me call this reference configuration R reference prime. You will see now it's a little bit different than what we did with objectivity. We'll do something slightly different here. What I do now, I take this piece of tree and I deform it. For example, I put it into some machinery and this piece of tree is being deformed. I don't know what you can do. For example, you could, let me just redraw again the with dashes, the reference configuration, just to appreciate the change of deformation of this piece of wood, of block of wood. So, well, imagine this was the reference configuration, and what I do now, I deform it. Yeah, for example, I do something like that. Well, it deforms in this way. It becomes like thinner. I just put it like, for example, below a testing machine and I compress it, yes? So it deforms in a certain way. It deforms like that. So let me say, for example, this is the gradient of deformation, yes? Well, in this configuration here, I will have a certain energy, yes? So this energy in this tree will be something, I don't know, will be an energy that depends on the gradient of deformation followed by this first path. Now, what is the idea at this point? Let's be careful. You remember in the discussion of objectivity, we were somehow rotating the current configuration. Here the things is different. The idea behind the experiment is the following. Let me imagine that I take the reference configuration, this one here, and before subjecting this configuration to my given state, which is characterized by f, I pre-rotate the reference configuration. So this is conceptually the difference. So let me pre-rotate it. I copy it. So I take my reference configuration and I rotate it in this way. For example, let me rotate this in this way. In fact, it is rotating. I should try to make it still, because otherwise I did another attempt before, but it was moving. So okay, now it's stopped. Okay, so you see what I'm doing. I'm taking the reference configuration, and this reference configuration, I'm now pre-rotating it before, let me say, doing the same experiment as before. So clearly the deformation between these two reference configuration is a rotation. So let me call this P. This P is such that P transpose P is equal to identity. In other words, P is an orthogonal tensor. And now what I do is the following. This is a new reference configuration, and this new reference configuration is what I call R reference second. And what I do now, I subject this body exactly to the same deformation of before. So for example, if before I was, for example, compressing along the fibers in this direction, I keep compressing in this direction. But you see, what is the difference? Is before you were compressing along the fibers. Now you are compressing perpendicularly to the fibers. So there is reason to expect that at the end, the deformation, the final state will not be the same. in general, right? So I take now this deformation F, exactly the same as above, and I deform this object. What will it be deformed like? Well, you see, this F is exactly the same that appeared here. So the same deformation, but I do it on two different configurations. One is rotated. Well, you see, intuitively, we can expect that the final state will be different, right? I mean, for sure, this will deform in something like that. It won't deform anymore as a chubby cylinder in which the fibers were all perpendicular. In this case, you see, in the previous example here, in this new configuration, there is reason to think that the fibers would remain aligned in this direction. But the thing now is completely different, because we can intuitively expect that the fibers will be oriented differently. What is the energy at a given point in this new state? Well, to characterize the energy, we can simply remember that in any case we are starting from the reference configuration here. So we can conceive this second path as a new deformation, let me say, and I will call it F bar, that brings the body from the initial configuration to this one. And I call this configuration, this deformation, F bar. So clearly, the energy in this new state is characterized by W of F bar. Now, what is F bar? Well, clearly F bar, you can easily imagine that F bar is equal to what? Well, how would F bar work? Well, you see, F bar takes fibers from this configuration and it brings them here. And if you were to follow this second path, you would be doing exactly the same. So you would first apply P, and then you would apply F. So you would be very easy to check that this F bar is in fact equal to Fp, if you agree with me. Because you see, if you apply this to a fiber, then first there is P applying to the fiber, so P brings the fiber here, and then F brings that fiber, rotated fiber, to the current configuration. So, is there any good reason to expect that these two final states will have same energy? Well, in fact, in this configuration, there is no good reason to expect that W of F will be equal to W of F bar, right? Because, for example, if I now do, let me do, for example, a second experiment, and to be more clear, I copy all of these experiments again. So let me call this experiment 1. And I want to do now a second experiment 2. So question, let me say here, is W of F equal to W of, instead of writing F bar, I can write Fp? Well, what do you think, intuitively? I give you some seconds to think. Do you think intuitively that the energy would be the same? But probably no. In this case, it's certainly unlikely. Yes? Why is it unlikely? But I told you before, because you see, if you were deforming a body with the fibers in this direction, certainly this body, when you compress in this direction, it is stiffer with respect to the compression when the fibers have been aligned in another direction. So if you do the same experiment here and here on two different configurations, the final state will certainly be different. But let me do, to go more into the thing, let me do a second experiment. In this second experiment, instead of rotating the body in this way, imagine that I rotate the body along the axis of the fibers. So for example, if the axis of the fiber is going in this direction, imagine that the new body, and let me copy this body again. Okay. So in this case, what I've done, well, in this case, the P that brings me to this configuration, to avoid confusion, let me call it, for example, P2, okay? In this P2, essentially what I did was, well, I've just rotated the body along its axis. So in other words, the fibers are always in the same direction. So now I subject this second reference configuration, which I call R second. This second reference configuration, I now subject it exactly to the same deformation of before, which is the one that it is written below here. So I subject it to F. Now what do you think? Well, the deformed configuration will be presumably very similar, if not identical, to the one that I have obtained in the first experiment, in the unrotated experiment, right? So in this second configuration, the fibers will still be here. And also in this case, I can compute again the total energy of this second passage, just like above. I don't go into much into the details since I did it before, but in this second case, F bar will be equal to Fp2. And here the energy will be W of F, and in this case the energy will be W of F bar, which is equal to W of Fp2. And now let me pose the same question as above. Is there any good reason to expect that W of F is in this case equal to W of Fp2? In this case, the answer is certainly yes. And for this reason, we call P2 a symmetry transformation at a given point. And of course, in the first example that I did here, the transformation P, which I could now call P1, and I should put 1 everywhere, P1. Well, clearly P1 is not a symmetry transformation, but P2 is a symmetry transformation. You start to realize that this idea of the symmetry transformations can be used to embed into the general expression of the strain energy density, W, some information on the internal structure of the material. So in other words, the P embeds information on the internal structure of the material. For example, we will see that in the case of wood, P has to be aligned in a certain direction. And in the case of other materials, this P shall correspond with any possible rotation. But this is very important because in this way we will be able to write expressions of the strain energy density for different classes of materials. Okay, I think I will conclude my lecture here, and this will be also the end of the lectures for the week. But please do get back on the, I will do a recap next time, but please get back into the main ideas, because it's very easy to confuse when working on these concepts. It's very easy to confuse between material symmetry and objectivity. The two concepts are very, very deceivingly related, but objectivity corresponds to a rotation of the current configuration. So it's a rotation taking place after, yes, the experiment. But when you talk about material symmetry, instead it's before. So it's a rotation taking place before. Keep it in mind, and we will go back into these details. So objectivity is used to reduce the constitutive dependence from 9 variables to 6 variables. And this holds always for any material, in any situation. Material symmetry instead tells you that the material, that the body, but at the local level, the material behaves differently, may behave differently. Okay, you could have, and in fact we will introduce next time the concept of isotropy or anisotropy, and because many materials behave in the same way in all the directions, we will call these materials isotropic, but other materials behave differently, like for example wood or fiber reinforced, for example, materials. Okay, but we will do this next time, and for now I hope it's clear. But don't worry, because I will go through these once again. Okay, have a nice day and have a nice rest of the week. Bye bye.